Hello, everyone. Welcome to the April 24th edition of Math 135. Today, we're going to be talking about two-sample t-tests that are not paired. So many applications of stats involve comparing two population means, men versus women, underclassmen, upperclassmen, U.S. citizens, non-U.S. citizens, people below the age of 50, people above the age of 50. In the previous class, we considered tests for differences where the means were taken from dependent samples. With dependent samples, we could pair the data and then consider the differences, D. But today we're going to talk about independent samples. So let's take a look at what that means. Two samples are dependent if each data value in one sample can be paired with the corresponding data value in the other sample. That's what happened when we took the paired test with the anxiety levels, people who looked at real pictures and pictures of spiders and people who looked at real spiders. Today we're going to be talking about independent samples where there is not such an easy way. There is no way to pair them. You've taken a sample from one population that's unrelated to the selection of the data from the other population. Let's say we want to know who spends more time on TikTok. We could take a sample of women and a sample of men. And the women we selected, the times they report, don't affect the times reported by the men. So independent samples will occur very naturally when we draw two random samples, one from the first population and one from the second population. Because the samples are random and they're from different populations, there is no pairing between them. So I'm going to give you a series of examples and you're going to figure out, are the samples dependent or independent? You survey a random sample of 100 of these students about the amount of time they spend on their cell phone each day. 65 are female, 35 are male. You compare whether males or females spend more time on their phones. Do you think it's independent or dependent? Well, if you said independent, you're right, because the time that women spend on their phones is not affecting the time men spend on their phones. They're different populations that we're drawing from. You survey a random sample of 100 of these students about the amount of time they spend on their cell phone each day. You then have them check their amount of screen time use on their phones for a week. After that week, you survey the same students again and about the amount of time they spend on their cell phones each day. 65 of these students are female and 35 are male. You compare whether students spend more time on their phones before or after examining their screen time usage daily for a week. What do you think? Do you think this is dependent or independent? If you said dependent, you're right. The data you collected was you got the data of the least students before how much time they spent on their phones previously, and then after how much time they spend on it after a treatment. So that's a dependent data from samples, and we would use a paired t-test here. Okay, so in order to do a test where we look at the difference of means of two populations, we need two random samples where you get two different sample means, two different sample standard deviations, and two different sample sizes. You either need to know that the sample sizes are normal or they're mound. If you can't do that, you need the sample size to be at least 30. In the context, we're going to have you guys state the null and alternate hypotheses, set the level of significance, compute the test statistic and p-value using Excel, and conclude the test, reject or fail, and then interpret the results. The interpretation's very important because that's the part where you're explaining your results to someone who isn't knowledgeable about all the statistical language. The conclusion is the most important part because that is the part that your boss is going to want to know someday when you investigate the data. They want to know what's the takeaway for them, not the details in the middle, whereas I want to know all of it from you. So we're actually going to be computing these using Excel, and because the formula for doing this is pretty terrible otherwise. Okay, so here's our first example. A random sample of male college baseball players and a random sample of college male soccer players, or I think it's supposed to say soccer, were obtained independently and weighed. The table below shows the data. The distributions of both data sets suggest the populations are roughly normal. Determine whether the difference of means significant using a significance level of 0.05. So here's the data, and I've already input it in Excel. I'm going to show you how do you do a two-sample t-test using Excel. It's going to be basically the same way we did a paired t-test, but there's going to be a different box that we check. So we go to Excel, and we see here that the data is already in. So we go to the Data tab and click on Data Analysis, and we do a t-test with two samples assuming unequal variances. There are some situations where you can assume equal variances, but we are not going to deal with that today. It's very unlikely that that will happen. So we click on t-test two samples assuming unequal variance. We highlight our first data, that is the baseball players. The other column, the soccer players. We hypothesize that their difference in weights is 0 on average, and we find an output range. And we run the test. And what you find is, if we look at the annotation, this is our test statistic. That's our t-value. Now, our alternate hypothesis was just that their weights are different. So we're going to want to use the two-sample part. So if I look here, I want the two-tail test. So I want the p-value for a two-tail test. So let's get some data values here. Let's see, let me format this cell so we can see decimals. All right, so we got our p-value. So our p-value for our two-sided test is 0.000145. That's really small. So our null hypothesis was that there was no difference in the means. And our alternate hypothesis was that there was some difference in the means. We don't know what it is, but that was our alternate hypothesis. We found that the p-value is really small, so we're going to reject our null hypothesis, and we're going to conclude at 5% significance level that the average weights of baseball and soccer players are different. So we're very confident from this that their average weights are different. What you see here is the average of the two columns. The 193.56 was the average weight of the baseball players, and the 175.45 was the average of the soccer players. And you could probably have guessed that these two average weights would have been different because soccer players have to run a lot more than baseball players, and so it's going to attract a different type of athlete. Okay, so we were able to do this hypothesis test using Excel, where it calculated the t-values and the p-values for us. All right, so let's look at another example now. Let's go back to our slides. We're studying a pathogen for bell peppers, and we think that somehow the water level in the soil affects it. So we're going to look at two fields where we're going to compare the soil water content for the two fields. So we have data for two different fields, field A and field B, and we want to know whether field A has on average a higher soil water content than field B. So let's look at the data. Here's our data, and I've already put this in Excel. So let's go back to Excel and state our null and alternate hypotheses. Well, our null hypothesis is that the two fields have the same average soil water content. I want you to pause the video and see if you can figure out what the alternate hypothesis is. What do we know about field A's average minus field B's in our test? Well, if you said greater than 0, you'd be right, because we think that field A has a higher soil water content than field B on average. So mu A minus mu B should be positive. So now we need to run our t-test, our two-sample t-test. We go to data analysis, t-test with 2 samples, assuming unequal variance. And we get our data for the field A. We get our data for field B. And we choose our output range. It's right here. So this was a one-sided test. So that means that our p-value should be right here. So a p-value of 0.0279. This means that we reject the null hypothesis at the 5% significance level because our p-value is less than 0.05. And what we conclude is field A has a higher soil water content on average than field B. All right, so in many ways, this is great that you don't have to do so many calculations anymore. The p-value is just calculated for you. However, now the task is to make sure that we interpret these conclusions, these numbers correctly. And that's the most important part of this lesson. Let me know if you have questions. Take care.